Hello, my name is Steven. Welcome to HiFinder Tech Talks, where we focus on understanding the technology that makes the hydrogen economy work. If you are interested in bipolar plates, there will be many nuggets for you today in this video, because I have a special guest who works for the big ones who make fuel cell systems and stacks. He is the CEO of Cellform, a chemist and an absolute expert in metal forming. Welcome, Simon Brugger.
Welcome. Hello, Steven. Thanks for having me.
Thank you. It's a particular pleasure to have you here. And I see you did not come alone. You also brought something with you. Can you tell us just briefly what you have here lined out on the table?
Yes, so we have metallic bipolar plates on the table.
Yes.
Here specifically for fuel cells. Bipolar plates are one of the main components of a fuel cell stack, as well as an electrolyzer stack, yeah.
Okay. And this is from a fuel cell, and this is electrolyzer or fuel cell?
No, both are for fuel cells in that case. The plates for electrolyzers are way bigger, so we're talking about 2 meters in length.
Oh, wow.
And I wouldn't bring that in today.
Okay. And this is a small one for the lab?
Yeah, that's for the lab, yeah. That's for coating testing, for sealing testing, etc. Yeah.
Okay, cool. So now we have this, but can you take us a little bit on a journey? Where would we find this in the system?
So bipolar plates are needed several hundred times for each fuel cell. So they are stacked together.
Yeah.
That's what it made a stack. And we have in between those two bipolar plates MEA, so a membrane who is actually the heart of a fuel cell, because the membrane itself. Let's take a look on the slide here.
Okay.
So we have one cross-sectioning. So the plate itself is showed here 2 times. So we have 2 single plates welded together. So this is a metal sheet, in most cases stainless steel, sometimes titanium, welded together.
So this dark section is essentially this plate.
Correct.
In cross section. Yeah. So we're cutting through. And we're looking through, and you say we see 2 plates. So we're basically seeing 2 plates kind of on top of each other.
Yeah. So in a real fuel cell, of course, 2 identical plates.
Yes. Yeah.
So, and one side of each bipolar plate is representing the anode side.
Yes.
So the one who gives the electron, and the other one is the cathode who takes the electron. And what happens here is actually the core of a fuel cell. So the transition from hydrogen to electrical energy.
These are the channels, yeah? So we have here water.
Yeah. So we have the water, so the closed channels between the 2 single plates are actually for the coolant channel.
Yes.
So a fuel cell is very picky when it comes to temperature, so they want to stay at a specific temperature level, and this is provided by the coolant.
Coolant, okay. So these are the coolant
correct.
channels. Okay. Okay. So in this case we have water as a coolant. Okay.
Yeah. And the coolant itself does not play a crucial role in terms of the functionality of a plate.
Yes.
What plays a crucial role is actually the side that we see on top of the plate. And that side, in that case, is on the anode side, it's hydrogen.
Yes.
So we're taking hydrogen inside the stack, and the fuel cell or the bipolar plate is responsible for the distribution of the gases. Cooling is one responsibility, distribution of the gases is one responsibility, and gases means hydrogen on the anode side and oxygen on the cathode side.
Okay.
And what happens now is hydrogen wants to react with oxygen to liquid water.
Yes.
And this liquid water then needs to be removed by the bipolar plate on the cathode side.
On this side,
And what is the idea behind the fuel cell, and what is the idea behind the bipolar plate in the end is that the MEA between the 2 plates is actually only permeable for protons, so for H+ protons.
Yes.
So the hydrogen needs to give one of its electrons to the anode side, going through the MEA and takes this electron from the other side and is reacting with oxygen to water. And this electrons actually is then transferred from the bipolar plate through an engine, an electrical engine in the end, who powers, for example, the car, and then the electron is then transferred to the cathode side. So that is the idea behind the fuel cell.
So what we see, this metal plate essentially is giving space for the coolant to come through, and then also holding the MEA in place, providing channels for hydrogen on the one side and channels for air with oxygen on the other side, and taking out the water vapor or whatever comes out of that, and also taking out the electricity. So the electricity flows through here. That's
correct.
where it comes from.
Yeah, correct.
Okay.
Yeah. So it needs to be electrical conductive to electricity.
Way to go. Okay, wow. So I know you build these things for also, you know, meaningful companies in this area. So what do they care about when you do this?
Oh, they care about a lot, of course. So first of all, quality, because we're talking about very, very tiny geometries in that case. So the foils are 50 microns, sometimes 75 microns. So here we have actually 50 microns welded together, and in that case it's 75 microns. So the thickness itself and all the quality deviation, etc., is very demanding. So that is the first they care about. And of course, in terms of the functionality itself, the bipolar plate plays a very crucial role when it comes to price and efficiency inside a fuel cell. So yeah, a lot of amount when you buy, for example, a Hyundai Nexo on the market. A lot of the price you're paying for this car is actually represented by the bipolar plate itself, because it's needed 350 times in that car. The price itself is mainly determined by the product.
Okay, so that means you are one of the people determining the prices in our industry.
Yes. And we are obviously trying to reduce that. So most of the customers care about the price, of course. This is one main disadvantage of hydrogen overall, price. So if you compare it to battery electric vehicles, for example, you need to reduce the price to a lowest possible in order to enable hydrogen overall.
Okay, obviously, well, price, you know, all these things come through efficiency and making production. Maybe can you take us a little bit into how you get that efficiency? What do you do to make it more efficient?
The efficiency is actually the second part I care about the most, because efficiency is also mainly determined by the bipolar plate itself. Not only by the bipolar plate, but it has a huge impact. So how you form those channels, and not only the accuracy, but also the engineering behind that strategy is actually plays a very crucial role in terms of the efficiency of a fuel cell. And efficiency itself, only to highlight that point, is also the second main disadvantage of fuel cells, because you need to, or of hydrogen, because you need to transform electrical energy to hydrogen. That is called electrolysis in a green world. And that green hydrogen then needs to be transformed back to electrical energy in the fuel cell. And both transformations, so electricity to hydrogen and back to electricity, both stages are actually comes hand in hand with energy loss.
Can you show us more about that? I know you have some things that you also brought with, some information, like how you manufacture, how you get those things formed and so on?
How we get those formed. We are starting with a thin substrate material when we talk about the manufacturing approach. And this could be stainless steel, it could be titanium, nickel basis alloys, you name it. So everything in the metal area. So there are many ideas on the market. And then we go into the forming. The formed half channels then, or the formed half plates, are then welded together. And this is in the end the final bipolar plate. We always need a coating on the bipolar plate, because the conditions inside the fuel cell are very rough for the metal. And after the coating, or also sometimes before the coating, we make a leak testing, because of course any leak needs to be determined before you stack it. And then the final stack will then be set up.
So essentially you take a flat metal and then you...
Correct.
I don't know the words, punch, form.
There are many forming approaches on the market. So conventional stamping, hydroforming, rolling forming, all those forming strategies have advantages and disadvantages.
And then you have to weld them. Why do you have to weld them?
Because you need to represent the coolant channel between the plates.
Because you need to stick them together. Those two, like we saw on the other picture. All right, okay.
That is,
and what is it that you coat them with? What do you put on them?
Mostly it's PVD coating or carbon-based coating. So the coating itself needs to reduce the electrical contact resistance on top of the plate to an absolute minimum. And also, the corrosion resistance is also a huge topic. So no metallic ions, they will destroy the MEA, of course.
When I look at this, this is very thin. So, I mean, doesn't this break when you try to coat form a channel, or like form a channel, all these things?
Yeah, that is actually the main task for us, because we're talking about very thin substrate sheets, the thinner the better. So 50 microns is more welcomed by the customer than 75 microns. And the thinner you get, the harder it is to form. Here we can actually see on that slide also some quality assurance we are doing on this plate on the table. So we have a cross-sectioning in that red area. And here you can see the thinning. And our task, of course, is to make the thinning very, very evenly. So you need to be able to evenly distribute the flow, the material throughout the flow field. So that is what the active area means on the bipolar plate. That is called the flow field.
So
and the efficiency, just to take up that thought, the efficiency increase is determined by how much flat area you have on top of it, how accurate are the channels, because the electrical current also needs to run, of course, through the plate. And if you have a longer distance, if you have less contact area between the plates, the more energy loss is actually happening.
So this top area would be the contact to the next.
That top area in that case is actually the contact area to the MEA.
To the MEA.
So we have the GDL, then we have the membrane, another GDL, and then the next bipolar plate. And
where would be the next bipolar plate?
The next bipolar plate would be here.
On this side,
So the next, so we're only looking on a half channel here, to be honest. The next half plate would be there, and then welded together.
And this is where you would do the welding.
Correct.
And how do you do the welding, if I may ask? Like you get in between there and weld.
Yes. So a common strategy is laser welding, of course. We can also look on some pictures here. First of all, of course, it's a very hard job to weld 50 microns times 50 microns together, because there is no material actually on the plate that you can use for any weld. The companies are actually doing that very, very good on the market. The task today is to be very process reliable, because the welding itself can destroy the plates. You can cause some defects on the plate. And you need to be able to do it very fast, because you want to reduce the price to a minimum, of course.
So looking at this diagram here, what do we see here? I mean, I recognize the channels.
We're only seeing a little bit of the plate. So only 2 channels. We're talking about 2 or 3 millimeters here. And the dots in the bottom of the channel are actually the laser welding dots. And that is some kind of 3D deep measuring we're doing here in order to look on the weld seam, in order to look on the weld dots, because you not only need to weld the plate around, because you need, of course, a leakage weld for the coolant channel. You also need some electrical contact welding in the flow field. That is also very, very crucial for the functionality of the plate, because a lot of energy needs to run through the plates.
When I think of that, that's the especially a plate at the end essentially is taking up the entire. Actually, all plates are taking up.
Correct. So they're aligned in line. So you have one big anode at the top of the stack and one big cathode on the bottom of the stack. And a lot of energy needs to run through
all
those
the
plates.
cells need to transfer all that what's being generated.
And that is why the plates needs to be in the best shape possible, because any deviation is causing some energy loss. Because the contact is not as the engineers of the stack originally thought of. And that is why theory and practical implementation are laying far from behind.
Okay, Simon, I need to ask it. So I mean, I've just idealized how these plates lie on each other, and I know you make these, and then you for the bigger stacks also. So in the practical aspects, what do we see? What are the challenges? How do you make it as near ideal as possible, and what happens that is not ideal?
So we at Cellform, I can only speak for my company, we have a multi-stage forming process. So we are able to form in several steps. So every geometry from our customer is actually engineered on its own. So of course we have some ideas that are always taking into account that forming strategy. But due to a multi-stage forming process, you're able to enlarge the design freedom, because you can foresee some crackings. You can push some more material inside those regions where cracks might appear. And the accuracy level is way higher, because you have so many adjustments inside those multi-stage forming processes. in order to push the material where you want it, in order to get some deviation areas of less than 10 microns actually. So less than 10 microns on the formed plate is actually some accuracy level you can achieve through our process.
Yeah, I know. 10 microns, that's, we're talking hair size.
Yes, yes. And on the final plate. So 10 microns in some areas is even hard to mill on the dies, for example.
Yes, yes.
And if you need to be that accurate, everything needs to be in perfect shape, of course. Not only the dies, but all the tool setup, everything needs to be adjusted perfectly together.
Yeah. Well, I asked myself, I mean, this is already a metal plate. What material do you use to actually then, form it into that? I mean, I know you mentioned that you go through this several times.
Yes.
But what kind of material is that can make such small channels?
Oh, the dies, you mean?
Yes.
Yeah, the dies are actually metal in our case.
They're also metal.
Yeah, they're also
different
metal.
Kind of metal,
Very, sorry?
Different kind of metal.
Yeah, different kind of metal, So no stainless steel metal, but some kind of very, very special tool metal in order to form the different stages in the end. Yeah.
Okay.
Yeah.
And you say to make it, form it fast and weld it fast. Okay. So how does one then at the end of your production, what comes up? You have them all welded together? This is one plate or is two plates? I think it's one plate.
It's one plate. It's one bipolar plate assembly. So we have anode and cathode welded together. So two single plates are in your hand.
Okay, so you would assemble the entire cell, the assembly. So you would put two plates together.
No, we at Cellform, I would say all the bipolar plate manufacturers on the market are actually producing the product you have in your hands.
Okay.
Coating is optional, some seal gasket is optional, but our customer want to take out the bipolar plate out of the package and then stack it together. So the stacking itself is done by the companies, by the big companies on the market.
Okay, cool.
Yeah.
Wow, okay, this has been really intense. Okay, and anything to add?
Anything to add? I mean, if we have some little bit of time, I think I can also show you some very disruptive idea in the welding area. I talked about laser welding.
Yes.
And laser welding is also the way we are actually welding it. But what is happening at Cellform is kind of a one-shot welding. So we have some R&D work where we actually are able to weld a bipolar plate in only one shot. It's like taking a picture of the plate.
Okay.
So not aligning all the weld seam on the plate, millimeter by millimeter around it, but weld everything together at only one shot.
So meaning not to go tick, 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 but just to go bam.
Correct.
And everything is welded.
Yeah, so we're talking about 0.004 second for a welding of a bipolar plate.
Oh, wow.
Everything for the price. It is something that is not really welcomed by the engineers, of course, but price is something that matters, I would say, the most in the hydrogen area.
Why not welcome by the engineers?
Because they don't want to talk about price. They want to talk about the best strategy engineering-wise. So they don't like the cost factor.
Well, I feel for the engineers, and it's been very exciting talking to you, Simon. I know, this is actually, as a price determinant in the industry, I challenge you, help us more.
Yes, we need it.
Let's get these better.
Yeah.
I think we've learned a lot. Thank you so much for your time. Unfortunately, we have already also come to the time that we have in this video. It's been an absolute pleasure. If you want to find products like this or even other components for fuel cell systems, please go to highfinder.com where you can get in contact with people like Simon who make these excellent products. If you like this video, please like or subscribe. Also, drop us a line on LinkedIn or wherever you can. And we will be making several topics in several videos, so feel free to watch another one. We'll be very happy to welcome you. Thank you very much, Simon, for taking the time to be here.
Thank you, Simon.
It's been an absolute pleasure. Have a lovely time further. Thank you very much.
Thank you.